Lesson 11.3. Well, let's get started on this bell ringer over lesson 11.2 when we were just looking at probability distributions. Number 1 says a sample of high school students were asked how many days they overslept last week. Use a frequency distribution to shown to graph the probability distribution for the random variable x. Well, before I get started here with this table, I'm going to encourage you to go open up your Desmos pre-programmed calculators, which I have here. And from this document, if you slide down to the bottom, open up your statistics calculator. So oftentimes in younger levels of math, I'll call it younger because we got there when we were younger students, we saw a table and we would immediately type these in as x and y. Well, what we've been doing the last few classes, we haven't exactly been dealing with this data right away. We've a lot of times been altering it first. And so on this particular problem, what I'm going to do is find the probability of each occurring. So the oversleeping 0 minutes, what's the probability of that? What's the probability of 1 minute? And all that value, all those values going down. And so just to help me see this a little bit clearer, let me add some lines in here. And what we need to do is come up with the sum. So we could use the calculator or even just to add them across. 12 plus 18 is 30, plus 10 is now 40, plus 7 would be 47, plus 11 would be 58, 61, 70, 75. I believe we have a total of 75 here. And so if I have my values correct as we go across, the probability of each one would be like on this first case, it would be 12 divided by 75. This one would be 18, whoops, 18 divided by 75. So this right here, the sum I got was 75. And so if we just went down, hopefully it did in fact equal 75. 30, 40, that would be 47. That would be 58. This would give us 61 again. If you were calculating the sum, 9 gives us 70, and 5 more gives us 75. Okay, so if we've done this right, the probability, the sum of this should equal 1. That would be the probability. Okay, so let's look at how this graph is. So instead of graphing the values they gave us, we're going to graph these. So oversleeping 0 minutes, 1, 2, 3, 4, 5, 6, and 7. We're going to look at those, and specifically the probabilities. It's 12 over 75, 18 over 75, 10 over 75, 7 over 75, 11 over 75, 3 over 75, 9 over 75, and 5 over 75. I'm going to hit the little zoom fit button right here, and we can see our data. Now here's the deal. It shows it to us as continuous data, this line here. But truthfully, what we were not looking at is if you overslept 1.5 minutes or anything like that. It was just rounded. It was shown as discrete. So you could actually edit this if you wanted to. If you hit the setting, you could change this value right here. Whoops, why isn't it working? There we go, edit. I'm going to click this value, and you could turn off the lines like this. You turn it off and you see just the dots. The point is like that, but I like the lines on there just to help me see this value a little bit easier. But ultimately, this needs to be discrete data. So if I were going to use these values and try to come up with the solution, it would be helpful for us to look at the answer choices. So here on this slide, I have the 4 answer choices, and I know this line graph appears really good. But again, this would be as if it were, these are the number of days, how many days they overslept. And I think I was reading that as minutes earlier, but this is how many days of the week they overslept. And you can't oversleep 1.5 days. So this would actually be out because that is continuous data. So this one is out because it's continuous. Even though it looks like our graph, we should be continuous. Okay, there we go. That's why this one is out. So we're really looking at these values. And now the probability, remember all probabilities have to add together to be 1. I can see that this chart, these values do not equal 1. Sum is greater than 1. So C is out. And when we look at these probabilities, okay, so now we're looking between these two. And we want to find the exact probability. It looks like to me that it would start at a little bit above 15. That's a little bit above 15. Ooh, this one's not. This one looks like it's just the number 12. They put that at 0.12. So that's value is going to be off. That was right here, 0.12. My guess is this one is going to be 0.18, and it is. You can see what they did on this incorrect answer is they just plotted the frequency as a decimal rather than actually calculating the probability. This looks like it's 16%, which I didn't even write it that way earlier. We could have come back and said, okay, that must be 16%. This one would be 24%, and so on and so forth. You could get all the values just by clicking through here. This would be 13.33%, 9.33%. Maybe I shouldn't, I speak too early. No, that was 24, that was 16. Okay, I just happened to get the decimals down. 4%, 12%, and 6.67%. So that's how you can do number 1 using that calculator. Now, let's talk about number 2. It says, find and interpret the mean for exercise 1. Well, we talked about last class quite in detail about the math involved to find the mean. But what I did not tell you is now that we're here, I'm going to go ahead and let you know, you can on Desmos type in mean. And what I'm going to do on here is, let's see, the mean of this data here. The mean, you can type in, actually, that's not going to work yet. Let me first come back over and show you the algebra here. So let's go back to the algebra. If you remember what it is, the way you determine the mean is you multiply the x value times the probability p of x. Let's write that in here. This is probability p of x. So what I could do is I would come in here and say, this is the expected value, is what we're trying to solve. If I did x times p of x, what we would get is 0 times this, which is 0 here, and then 1. So this is my x, and I'm multiplying it times the probability p of x here. 1 times this is 18 over 75. 18 over 75. Sorry about that. Pen problems. And now the next. Whoops. Okay, let's try this again. And then 2 times 10 over 75 is 20 over 75. 3 times 7 over 25, whoops, is going to be 21 over 75. And then over here, 4 times 11 over 75 is going to be 44 over 75. 5 times 3 is 15, so that's 15 over 75. 6 times 9 is 54, so 54 over 75. And finally, 7 times 5 is 35, so 35 over 75. And now the mean we learned, the mean is equal to the sum of the x times the probability of x, the expected values here. It's the sum of these expected values, or the expected value itself is the mean. And so if I add these up, and that will be our mean here. So I'm going to come back to this in a second. So what do I have? And I'm going to add this as a new list. Let's just call it M1. So the expected, I have 0, 18 over 75, 20 over 75, 21 over 75, 44 over 75, 15 over 75, 54 over 75, and 35 over 75. How many lists here? There's 8 total. From 0 to 7 is 8 total. So there's 8 total here from 1. And here's a trick, the length of x1 So that means it's just going to run all these numbers in here. And what do I want it to add up? I want it to add up the M1 list. So you type N1 and then you do this little N like this. And it says the mean is 2.76. The mean would be 2.76. That's the expected value, that a student would oversleep 2.76 days in a week. So let's come over here. 2.76 is answer choice C. And the standard deviation, which we can go through the algebra for, but again, there's ways of doing this in the calculator that would be much more beneficial. All right, now let's talk about how using the calculator we could come up with these values. Now there's little codes here that you could type in, like mean of y1, for example, and it'll give you the average of this data set. But if we don't have the data set up there, you'd have to do a little trick. And so what I'm going to do here is walk you through. We found the mean by finding the sum of all these different probabilities. And I called that M. I probably, now thinking about it, would have been wiser to call it P, probability. Let's call it probability. And so I need to change this now to a 1. And so that was our mean that we found. Now, if you wanted to find the standard deviation, or rather, let me start with variance. If you wanted to find the variance, if you remember the formula, you have to take your random variable and subtract it from the mean. You square that value, and then you multiply it times the probability. So now that we know the mean, you take 0 minus that, and you would go all the way across here. I'm going to let the calculator handle this for us. This would right here equal the variance, which is sigma squared. So that's our formula. Here's what I'm going to do. I'm going to come over here and basically type in the same thing here. Let's have sum, and we're going to go from 1 to the length of x1. That means it's however long this list is, it's going to continue to add the sum together. And what we're going to do is we're going to subtract the x1 value, x1, and here's how you work with lists. You use this bracket here, and I'm going to put the letter N. That means it's going to plug in, when N is 1, it plugs in there. It says, what's the first number in the list? And then it'll plug in the second and the third. The reason it's 28 is because it's 0 plus 1 plus 2 plus 3. It's adding those all together. What I'm going to do is I'm going to take that value, and I'm going to need to subtract it from the mean, which we got the mean to be 2.76. So each value minus, oops, I put 2.76. There we go. And now we need to square this. And then we're going to times it with the probability, which is P1 of each value. And I get this as my variance. My variance is 18.76. So if you needed to know the standard deviation, you would take the square root. The square root of that 18.766976. That's going to be our standard deviation. And so when I come back over here, it looks like my values are a little bit off. Let me check what I did wrong with my formula real quick. Very simple mistake here. That was not supposed to be the probability. This was the probability here. So when I come over here, I need to name, there we go. Now I have that as my variance. I'll call it V. And then I'm going to take the square root of that variance, and I get 2.2. So very simple mistake I had there. I can check it. The sum of my probabilities is 1. That's good. This right here, to find the mean, needs to be a 1 again. So there's our mean. Okay, so that was my problem, is I wasn't multiplying times the probabilities. I was multiplying times the expected values when we were calculating that. Now I have my numbers right, 4.93 and 2.22 for my standard deviation and variance. Variance and standard deviation in that order. The symbols one more time. Let me go ahead and write this over here. That would be my variance symbol right there. My variance would equal 4.93. 9 to 9, and I'm approximating. And so the standard deviation is the square root of that, which is approximately 2.22. And let's take a look at now number 3. It says, which situation describes a binomial experiment? Now, in binomial, just remember that means there's 2 outcomes. No matter what, there's only 2 outcomes, and you perform an experiment a whole number of times. So let's see, I toss a coin 10 times, so that's a whole number, to see how many heads occur. Well, if you toss a coin, there can only be heads or tails. That sounds pretty binomial to me. 2 choices. There's either heads or it's going to be tails, one or the other. So this one looks pretty good. Let's check the other one. You ask a friend how old they are. Well, if you ask me when I'm making this video, I would say 35. I ask you, you might say 17. Someone else might say 18. Another might say 16. Notice there's a whole lot of options there. So it's not binomial. I try to guess a student's height. Well, I might look at you and say, well, you're kind of shortish. So I'm going to say 4 foot 1 inch. You might say, that's right. Or you might say that's wrong. What do you think? Well, it's either right or wrong. 2 answers. Well, no, because I might guess a different student, say, you're kind of tall. You look kind of like you're 6 foot 11 inches. Well, I can be guessing, and notice I have all these different heights. So no, that's not binomial. Let's see, I roll a die until 6 appears. Well, I roll it and I might get a 5. Maybe I get a 3. Maybe I got a 6. Notice there's 3 different options there. So the answer choice would be A. Let's take a look at lesson 11.3, the normal distribution. Wow, this lesson's pretty cool. So what we've done in the past is we've analyzed probability distributions for discrete random variables. Now we're going to find values that are normally distributed over curves. And this is pretty neat. What it's saying is, in a normal distribution, things seem to happen pretty symmetrical. And we'll have all these terms you'll hear a lot. You've heard the normal distribution. We're going to see that a lot. So I'm about to show you a normal distribution in a moment, but it says this: the graph of a curve is bell-shaped and symmetric with respect to the mean. So if you open up normal distribution here, I'm just going to give you an easy one. The standard is 0, 1. I'll show you what the picture looks like. What it says is, if the mean of some distribution is 0 with a standard deviation of 1, you'd have a graph that looks like this, where if you plotted all the different random events that happen, if you had a whole bunch of data, 100 people did something, the values that would occur would look like this, where the value 0 would occur about 40% of the time, and the value 1 would occur. You can add all these up. Now, the area under this curve is equal to 1, which means if you had an infinite number of the samples and the average value was a 0 with a standard deviation of 1, and you plotted them in, you'd have a graph that would look like this, where all the values would be plotted in within here, all the different options. Every time someone was a -1, it added a little bit. Every time someone was a 0, it got higher and higher. You would look up and it would have this graph, and underneath it, the area from the x-axis to this curve would equal 1. That's what it's saying here. The mean, median, and mode are equal and located at the center. This curve is continuous. The curve approaches but never touches the x-axis, so it never actually gets there. It just gets closer and closer. And the total area under the curve is 1, like I was saying. So here it is. And what we will learn is, if this is the mean, that's the mean, this is 1 standard deviation. 1 standard deviation to the right will have 34% of the data. 1 standard deviation to the left will have another 34%. So between 1 standard deviation left and right, 68% of your data will occur. Between 2 standard deviations, you will have 95% of your data. That's the kind of like definition, or the empirical rule for a normal distribution. That's how they line it out. When we find our values, it's by definition, the normal distribution, 95% of the values will occur between 2 standard deviations. That's how we'll come up with our math. And then within 3 standard deviations each direction, we will have 99.7% of our data. So here is an example. It says the heights of 32 peaks in a mountain range are normally distributed with a mean of 10,200 feet and a standard deviation of 295 feet. Approximately how many peaks are more than 10,495 feet tall? So here's the idea. We have 32 peaks, that's how much the sample is, with a mean of 10,000, type that in over here, 10,200, and a standard deviation of 295. 295. And now I'm gonna hit this zoom. And so here's our normally distributed data. You might notice that if the mean here is 10,200 feet and one standard deviation is 295 feet, that the value 1045, that is the mean plus one standard deviation. If you added these two together, and the mean plus one standard deviation would be 10,495 feet. So that's why on this graph, this is right here, the mean. That's the mean. This is one standard deviation. This point right there is the mean plus one standard deviation. The x values I'm talking about here. So it would be better if I labeled it here. Let me do it that way. We want to know how many events would occur out there. So how do I calculate this in the calculator? What we're going to do is, if you have this submitted in, what we can do is say we want all the values that are greater than 10,495. And so underneath in this min and maximum, if I put 10,495, you will find all the values that occur that are greater than that, which happen to be about 15.87%. Or I'm going to just say 15.9%. How many peaks are more than 10,495 feet tall? Approximately 15.9% of the peaks are taller than 10,495. And that's because it's one standard deviation over. So remember from this slide that one standard deviation is 34%. So you have 34% right there. And from the from the halfway point over in all of this area, you have 50%. So if you added that together, that is 50 plus 34, which would be 84. And if you subtract it from 100, it would leave you with 16%. And that's where we get this number. This is just more exact here. So about 15.9%, or you could even say 16%. I'd be okay with that. All right, let's try part B here. It says the heights of 32 peaks, the same situation. This time, what percent of peaks are between 9,610 feet and 10,790 feet? So again, let's think through the math here. They told us the mean, the average value is 10,200 feet. And we know that one standard deviation is 295 feet. So this looks like, from the picture, it's 2 standard deviations. So let's just say we wanted the mean minus 2 standard deviations. That would equal 10,200 minus 2 times 295. Well, 295 times 2 is going to be 590. And so if you subtracted 590 from this amount right here, that's where we're going to get the 9,610 feet. Just the same, mean minus plus 2 theta, or not 2 theta, I'm sorry, 2 sigma, is 10,200 plus 2 times 295. So 10,200 plus 590 is going to equal 10,790 feet. So that's where these numbers are coming from. This is our mean. That would be the mean plus 1 standard deviation. This is the mean minus 1 standard deviation. This is 2 standard deviations. So if we think about it, we should have 34% of our data here. And if I go back to the chart, 13.5 and 13.5 here. Now we'll see how when the calculator does it, it'll do it exact. But this is 68, and then you add another 27, which is going to be approximately 95% of the data. Let's see here. We want to go this time from 9,610 feet to 10,790 feet. This is, the calculator says, a 95.4% of our data, 95.4 of our data there. Okay, your turn. So given this problem, we want to know how many cars. So there's something, let me see, what percent of peaks? So mine was saying percent of peaks. If you need to know how many peaks, you could take your total here, the percentage. You could say 95.4%. This will help you, times the 32.954 times 32, which is approximately, this is between, this would say between 30 and 31 peaks have heights between those values. So that's how you would interpret this data. And on the previous one, when we got 15.9, we would say 15.9% times the 32. Let's see how many peaks this is. We take 15.9 times that by 32. Whoops. 0.159. So 15.9% times 32 is around 5. About 5 peaks. Greater than 10,490 feet tall. So that's how you assess your data. So you'll need to do the same on this problem. Let's take a look at example 2. So example 2 has to do with this very important factor called the z-value, which is dealing with how many standard deviations a particular value is from the mean. So here's our formula. You take your random variable, you subtract the mean, and then you divide by the standard deviation. So our formula, I'm going to go ahead and write it again. The z-value, and because some people say my z's look like 2's, I'll put a line through it, is going to be the random variable minus the mean divided by the standard deviation. So in this particular problem, we would have 36 minus the mean of 40 divided by our standard deviation of 6. So 36 minus 4 is -4. Divide that by 6. I'm getting -2/3. Or approximately -0.67. Be 6 repeating. So what does that mean? That means 36 is 2/3 of a standard deviation to the left of the mean. That's what it means. So if you had the mean here, the 36 value would be 2/3 of a standard deviation to the left. So just to kind of give you a better idea, here's your mean of 40, a standard deviation of 6. Let's remove these values here. The value 36 would occur almost not even one whole standard deviation to the left. The value 36 would not even be one standard deviation to the left. So one standard deviation would be 6 over, which would get just to 34. If these are counting by 2's, this would be 34. 36 is within one standard deviation, but left of the mean. That's the idea. So on this one, let's do this again. Find x. So we know, here's the formula again. Z is equal to x minus mean, the random variable minus the mean, divided by our standard deviation. So in this particular problem, they gave us the z value. So z equals 1.5 equals x minus the mean at 1.3 over our standard deviation of 0.6. So we need to do a little algebra to solve this. So I'm trying to isolate the variable x. So I'm going to do the opposite operations of what I see. What's the opposite of division? It would be multiplication. So I'll multiply each side by 0.6. So 0.6 times 1.5, I believe will be 9 or 0.9. Let's see, 0.6 times 1.5 is 0.9. That's correct. So 0.9 equals x minus 1.3. When I add my standard deviation, I will have my random variable isolated and won't be so random anymore. When I add these together, 2.2 is equal to x. And that would be my value. So this is saying if the mean was 1.3 and we had a standard deviation of 0.6, this value would be to the right of it, so it would be greater. And that's why we got 2.2. It's to the right. It's greater than 1.3. Your turn. Find z, given the random variable of 52, a mean of 58, and a standard deviation of. Why do we need that from example 2? Like, why do we need a z? Well, here's what a z does. So we're used to the normal distribution. A standard normal distribution is a normal distribution in which your mean is 0 and your sigma, or your standard deviation, is 1. And so here's a standard normal deviation. So notice the mean is 0 here. And this would be 1 standard deviation. So this would be mean plus a standard deviation. This would be 2 standard deviations, and so on. Well, if you're using the letter z, you can use the standard normal distribution and you just put it on the, let's call it the z-axis here, where each standard deviation is referred to as a z-value. So 1 standard deviation is a z-value of 1. 2 standard deviations to the right would be a z-value of 2, and left would be negatives, and so on. The same percentages apply. So that between 3 distributions to the left, standard deviations to the right, I said distributions, I meant to say standard deviations, you will have approximately 99.7% of your data. The total data would be, total percentage would be 100%. It's symmetric. Mean is 0, standard deviation is 1, like I said, and this curve approaches but never actually reaches the x-axis, or z-axis if you want to think of it that way. So here's an idea where you can see it both methods. It says here this salesperson keeps a record of the phone calls he makes to prospective clients. Over a 60-day period, his average calls per day is 20. So that's his mean. His mean is 20 with a standard deviation of 4. That would be sigma. So let me go over here to normal distribution, and we'll say the mean is 20 with a standard deviation of 4. Now I'm going to pick up the problem again. It says find the number of days in which the salesperson made more than 25 calls. Let me zoom fit this. So if I want more than 25 calls, I'm looking over here from 25 on to the right. So that would mean the minimum would need to be 25. And the calculator tells me that would be about 10.6% of the time. And I'm going to slide up. I already have these pictures here. This data, that's about approximately 10.6% of the time we call there, or he calls, makes more than 25 calls. So 10.6% of the time he makes more than 25 calls. So if you multiply that times the 25, no, excuse me, that's how many days we're here, times the 60 total days, we'll find out that approximately, or how many days he approximately makes 25 or more calls. Let's take that 0.10, 564,977, I'll just stop there, and multiply that times 60. We find out that it's approximately 6.3 days. So out of those 60, 6.3 of those days, approximately, I know that's weird to say 6.3 days, so maybe we say about 6 days, he made 25 or more calls. Now, let's use the z-value. If I wanted to use the z-value, what I would do is I would say z equals my number here, that's going to be our x, our random variable is going to be 25, minus the mean of 20, divided by the standard deviation of 4. That's 25 minus 20 is 5/4. Okay, so what this means is we could also use a standard normal distribution, which means the mean is 0. The mean is 0. The standard deviation is 1. And we could use the z value, 5/4, and we should still get the exact same answer. Let me redistribute this. There it is. We still get that 0.1056. So we would get, notice these answers are exactly the same values. So let me now pull up this graph so you can see them side by side. You can see that ultimately the data lines up perfectly, that the distributions are exactly the same for both the first that had a mean of 20 here, a mean of 20, and this one over here that had a mean of 0 with the standard deviation being a 1 value, and this one the standard deviation being 4. Notice this data concerns, if you went over here, this would be the day 25, or I should do it down here. That right there would be 25, and on this graph, that value right there would be 5/4. So that's how they correspond to one another. Now, so given that information, you can now use either a z-value, or you could just use a normal distribution that I've created for you in this statistics calculator to come up with your answer to DOL number 3. All right, example 4. Let's kind of look backwards now. Let's talk about what if we were given the area and we wanted to find the z-value that's associated with that data. Okay, so reminder with z-values. With z-values, we say that the mean, this middle symmetrical point, is a mean value of 0. Okay, so that's the mean value of 0. We want to find what z-value will give me approximately 75% in the middle, which means that this whatever z-value is here, this will be a negative z-value on this side. That's such that I have 12.5% on each side. So let me show you how my calculator walks through it. So for a z, you're dealing with a mean that is 0 and a standard deviation that is 1. So I'm going to zoom in on this, and now I'm going to introduce you what I did not have turned on before, but now you'll see the rest of the way, is what we call the cumulative distribution function, which is going to be graphing how much area you'd have at any point in time. So on our value, we want to know when I have 12.5% of the area over here and over here, and I truly want 75% in the middle. Now, some students will incorrectly think, oh, I need to put in a negative 1.25 to have it on this left side and a 1.125 on the right side. That will give me my value. No, that's not correct. You can see the pictures don't match at all. So that's not it. So what do you do going backwards? It's something like an inverse. It's kind of like it's the inverse of this cumulative probability here. And so how does it work? Well, using this value, you can figure out where the value would be by looking at our A value and this number of tails. That's what I'm doing. Slide down where you can see this A and number of tails. So what is number of tails first? When you hear me say number of tails, it's talking about shaded regions here. And you're going to hear me use this term a lot in the coming days. Is I'm going to say there are 2 tails of data that we're looking at. So I'm going to take this value over here and make sure it's on 2. And now my A value is going to be the area or the percentage of that outside area. So A is going to equal 12.5% plus 12.5%, which is equal to 25%. Or we could say A is, for the calculator, 0.25. And that's what I'm going to type in here. A is 0.25. Now what happens is this calculator here is going to show you that the z-values are going to be these locations where these meet on this graphed cumulative density function here. And so to get 0.125 And 87.2, if you're wondering where's 87.5, it's 12.5 plus 75% is 0.875. You would have the x values or the z values of 1.15. So that's what my answer is going to be on this one. Z is going to equal 1.15. Now you might be thinking, well, one of them is negative, one's positive. Yes, the negative one is negative z. So negative z equals negative 1.15 and positive z equals 1.15. You know what that means? If you divided this by negative 1, that z is ultimately positive 1.15. So that's our answer here. Now, could we have done this another way? Yes. If you come over and you look at this z-score, I've already found that for you. As soon as you put in this alpha here, the z-score, that's what's calculating here. These are the z-score values. So in this particular case, we get that those 1.15 is the left z-score value was negative 1.15, and the right z-score, that means what z is on the left and the right, or 1.15. So let me show you this all over again so we can see it afresh. Part B says, find the z-value associated with the top 5% of data. So again, we know that the mean here would be 0. Anytime you're dealing with a z, that means the mean itself is 0. You want to find just the top 5%, which means this is only one tail. The data is only looking on one side, and so A is just simply 5%, that one side, which we could say as 0.05. So when I come over here to my tails, I'm going to change this. I'm looking at one tail, and I want 0.5. This is giving the values if you want the far left or the far right, where I'm getting 1.645 is z. This z value right here, that z value would equal 645? 645. Now let's come over here to the z-score and you look at it. If you wanted the 5% on this side, that would be your number, negative 1.645 is how they ran it. And when I clicked on the button, that's how they rounded it to the nearest thousandth. But to the nearest hundredth, it would be 0.64. And then the same occurs for the positive side. If you want the top 5%, that would be your z value. So, you know how they normally list it. I should show this. Find the interval. Since it's saying the interval associated, you would just say that z is less than 1.645 is how I should have set it as an interval. And so let me go back. Did that one say interval? It did. So that's my z value. That means my z's need to occur between negative 1.15. And so I'm actually going to write this answer as negative 1.15 is less than z, which is less than 1.15. That's actually the way the answer would need to be written here. I messed up. I'll just have to erase that. Putting that boxed around the 1.15. That's not an interval, that's an exact value. So let's make sure we get the answer in the right form. That's what z equaled, and so we want the z value to be anywhere in between those two values to get the 75%. So now that you've seen it twice, I'm going to let you try on this one, see what you come up with. Pause the video if you need more time. 6, let's talk about probability. So what is probability? Probability is this area under the curve, this shaded portion. So on 5A it says traffic, the number of cars that pass through one intersection during a specific hour of the day is normally distributed. So I'm still in normal distribution here. And it gives me a mean. So I'm going to go change my mean value. This is in mean, comma, standard deviation. So my mean is 1,210. That's the average number of cars. And the standard deviation would be 220. That just means if you add 220 or subtract 220, you'd have 68% of the data. 68% of the time, you'd have a value between 1210 plus 220 and 1210 minus 220. Okay, so we want to know what's the probability of having between 1,000 and 1,420 cars. Well, that is simply, let me align my data here. That is simply, you put 1,000 here. What's the probability between having 1,000 and 1,420 cars? Since cars is the mean, you can plug it in as the min and the max. And it's saying what's the probability? It's this amount of area. Whatever the area of all of this area shaded is the answer, which we're told is right there. It's approximately 66% of the data. So this is approximately or I don't have to do the approximately symbol after doing that. 66% is the probability. So the way you would actually write that is P of 1,000 probability of the random variable x being between 1,000 and 1,420 is, now I would do the approximately symbol, 6.66 is how you would actually write that out. So what's the function that occurs here? Well, if you wanted to, you could say n1 is this normal distribution. You could write all this out, but since I said n1 equals, I could just say n1 dot CDF, which stands for the cumulative density function, and I can put my values in here, 1,000, comma, 1,420, and you would see that that gives us that same value as well. That would be the math that you would type in there if you wanted to solve it that way. So just really quickly, I'm going to add this picture in because I think it can be helpful to see it. It's just really large, so let's shrink it down quite a bit. There you go. And let's look at part B. It says the number of cars. Okay, so the same situation. We want to know what's the probability that x is less than 950. That means 950 is the largest amount of number. So I'm now going to move 950 over here to the right side, and there's no minimum, so I'll just leave it like that. And over here, if you were going to type this in, you can't have a negative amount of cars, so I'll put a 0. If you were going to actually type it in the calculator, you'd have to do it like this, 0, comma, up to 950 cars. And you can see that, again, this is the same number. The probability of having 950 cars or less drive through the intersection looks like it's just below 12%. So let's go ahead and add this picture in there. Here, the probability of having less than 950 vehicles drive through that intersection is approximately, I'm going to say 11, I'll just use their decimal, 0.1186. Now I want you to find the probability, given the situation, that the number of flowers is less than 30. Example 6. Let's find some intervals of data. It says weightlifting. Maximum bench press weights in pounds in a local gym are normally distributed with a mean or an average lifting weight of 265 and a standard deviation of 45 pounds. If a weightlifter wants to be in the top third, what must he press? So we're looking for how much would he have to lift to actually be in this value here. So let's go and plug in our numbers. We know that the mean in this situation is 265 and the standard deviation is 45 pounds. I'm going to zoom fit our data. And so I want just this top third. Notice this is one tail. That's one tail. And the A value is 1/3. I'm going to do it like that so it's exact. So I'm going to come to my calculator and say it's A is 1/3 with one tail. So here are the z-score values, and I'm going to put this as an x, so it gives me my graph again, and I need to actually adjust this so I can see as high as 1, because cumulative function only goes up to 1. So you can see this would be the value right there. That's the value indicating the weight at which we would be is 284 pounds. So he must be able to press at least, and since there's decimal, I would say he needs to be able to press, he needs to be able to press, I'm going to go ahead and raise up a pound, press at least 285 pounds. Now you might be thinking, how did I just get that? I went one tail at 1/3 and it produced this value, which was shown right here on this picture. Now, if you did not want to use that picture, could you have used something else? Yes, using this z-score. So that z-score is going to be finding out what the value, the percentage is right there. And you would have to work backwards trying to multiply it out times this weight and the standard deviation. So let me actually try this. Before I speak, let me make sure this is accurate here. 4.307. I'm just going to stop there. That's the z-score. So if you were looking at it, this being 0 and 1, this would be 0.43 of that one standard deviation length. Well, this standard deviation is actually 45 pounds. So I'm getting 19.38. That would be the standard deviation to get you to that point right there. I took that 0.43, times it by this standard deviation of 45, kind of scaled it out, and then you would add that to that mean. So the mean plus that 19.3815 gives us 284.382. Look how close we are there. You can see that's another way of getting the same value. All right, let's try part B here. Part B. Maximum bench press weights in pounds in a local gym. Okay, same information. It says, what range of lifts will put the lifter in the middle 80% of the distribution? So looking at this graph, there are two tails that are, it doesn't matter if they're included or if they're the part that's not included. It doesn't matter. But we say there's two tails. Two tails. Okay, and so the A value is the area on the outside, which would be 20% or 0.2. So what I'm going to come over here and do, now let me delete this, is we're saying A is 0.2, but there are two tails. And I want to know, same situation, I want to know this middle 80%. And so this time it's giving me these z-score values, but if I look, if I can lift anywhere between these two weights, I should be in the inner 80%. So if this is 10%, this is 10%, by the way, just to make sure we're clear on how we get to 100. This is 10% here in the data, 10%, and this is another 10%. 40 and 40, all that adds up to 80. 80 plus 20 is 100. Okay, so how much weight would this person need to lift? Anywhere in between 207 and let's say 322 pounds. You might say, why did you not round up? I could have, but I'm really wanting in between, and since I'm treating it as a whole number, we'll put the lifter in the middle 80%. Okay, so how else could I have done this? Well, we typed in our values, and I see the z-score come up. So that means I need to take this, and that is it. The z value you use if your standard deviation is 1. It's not right now, it's 45. So I would need to actually scale this z-score value out. So 1.28 times my standard deviation of 45. That's what I would need to add and subtract to 265. By the way, the negative will give me the same value, just a negative. So I would take my median, or my mean and median are the same thing on a normal, and I add that 57.6, and see we get 322.6, and then I would do the same thing, but 265 minus 57.6, 207.4, 207.3. You can see how similar they are. Anywhere between 207 and 322 pounds will put us in the lifter in the middle. So you could also use, you see how they use these symbols? I could just say x 207 needs to be less than x, which is less than, I'm going to say now 323 because I'm using the less than symbol. It's not equal to, so to be within here, I would need to be greater than 207, but less than 322.67. So less than 323, counting in whole numbers, would work right there. And I'm going to go ahead and just put 323 just to be consistent. And on the previous problem, you would say x needs to be greater than or equal to 285 pounds. That would be the answer this time. Okay, now you can try this problem here.